Welcome back, everybody. And our next presenter is Guilhem Molines from IBM. Guilhem is our frequent presenter in several decision camps, and he is a decision chief architect at the IBM ODM project, and he also has been involved in the navigation system of the unmanned Mayflower ship, and today his focus is on knowledge modeling and business user experience using machine learning and business rules. And Guilhem, looking forward to your presentation.
Thank you, Jacob, and thank you for having me in this conference. It's not the first year that I'm coming over, and it's always I'm always spending a good time here. I appreciate it. Indeed, last year I did present about Mayflower, so this year I figured I would take a different example to cover my topic. A couple of things. I only have one screen here, so if you have a question that you're posting to the Q&A, I will probably not see it. If it's a short question to understand something that I'm saying on the slide, don't hesitate to interrupt me, or Jacob, please relay the question. If it requires a long answer, maybe we'll defer it to the end.
Okay.
Just because I can only see what I'm showing to you, so I want to make it clear that I'm not able to see the rest.
Okay, no problem.
For those who don't know me, this is me. I've been working in the area of decision automation for a long time, initially with iLog rules. Then that company was acquired by IBM in 2009. The product has been renamed ODM. And 2 years ago, we've also added another offering to the suite of products called ADS, Automated Decision Services, which adds a capability for machine learning, which is really what we want to talk about this year in the conference. It's the main theme. I could see that from the agenda of the conference this year. You got my links at the bottom, so don't hesitate to reach out if you wanna discuss this further. All right, so in order to set the stage and try to describe a little bit where I want to go in this presentation is not a fully well-packaged scenario, demo, description of something that is completely made up, completely researched, completely, ready for production or anything like that. This presentation is more a talk about where we should be going, where we could be going to increase the transparency of the decision taking, especially with the newer challenge of machine learning integration. And for that, I'm using an example, which I'm going to present on the next slide, and show a little bit what are some of the challenges and what are some of the solutions we can put in place to help with the transparency. So the reason for that is we've always claimed within our community, and it's a well-known added value of rules, that they give us some value over code, at least for the business part of the logic, not really the plumbing, but where the business wants to express the logic that they want to see us program into their system, that the value is really around the transparency, because we expose the rules to the business, the traceability, where we can actually show when a decision has been taken based on what it's been taken this way, the explainability, right, which describe why a decision was taken a certain way. Those are really value, and in today's world of ML, there are words that are also coming to the front of the stage, because they start to ask us different questions. So this session is really a talk about that, about how do we retain or increase transparency in an ML plus rule world as compared to just a regular rules world, which we all know well and love and have been using for a few decades now. So I'm not using the Mayflower example that I've used last year. I'm using another example of a real customer that I've been working with for the past few years, that is looking at a use case where they want to fight financial transaction fraud, right? And the way this customer is doing this, the way they want to fight the fraud, is by applying a series of rules or observations on top of several types of data, right? First is the data that is coming within the transaction, right? What is the amount of the transaction, the date, which currency is the transaction taking in, basically things that are given to the decision-taking engine. And I'm purposely saying that instead of rules runtime, because it does include ML. So data that is given as an input, clear data. Then there is a context in which this financial transaction occurs, which can be information that is related to the incoming data, but not directly included into the incoming data, right? When the decision service is being called, basically, the amount or the currency are given, but there may be additional information that we need to go fetch that is not included, such as what was the contract? In which countries is the transaction happening, source and destination, right? Exchange rate, etc. Right? So information that we can go and get. Then there's also another type of data that can come into play is a bunch of aggregates, like maximum spending that occurred in the last X days, sliding average, peaks, threshold, etc. That is additional information that may be needed to decide, but it is not immediately either in the transaction or that cannot be gotten from the transaction directly without some additional computation. And finally, the last category, and this is just me trying to group them into categories, is information that is basically coming from ML models, predictive information like predictive score, risk score, propensity of a certain merchant to be conducting bad business or these kind of things, right? So I classify the data this way because you can see that there's a notion of distance between where you're taking the decision and how you get the data. The data that you have that is given to you as an input, so accessing it is just immediate. It's right there as part of the input set. There's data that, in order to take the decision, you may need to go and fetch from some external system, or you may need to get from execution of an ML model that has been previously trained for that purpose. So the data that can be cheap or more expensive to get close to the processing or further in the sense that it takes more effort to go get it. And there's also another notion, which is the complexity of the data. There's data that is simple, you just read it, or anybody can understand it, like the amount of a transaction or the date at which the financial transaction occurs is something that everybody understands. And there may be data that is very specific, some aggregates, some scores that are only making sense for experts in this business for a specific case, for a specific fraud pattern that we need to block. So all of this makes it so that some data is much more costly to obtain than others, other data elements, and much more difficult to obtain and much more costly in terms of CPU time. And guess what? When we do transaction processing, speed is quite important as well. So it is important to be able to take a decision that is both as correct as possible, that exposes the banks and the financial institutions doing the transaction the least possible, but that also tries to cover for the maximum number of potential fraud patterns that you want to detect. So how do they implement that, right? So we are architects, we like pictures. Here's a picture. The way it was implemented is that on the top, you see a transaction object coming in. So there's a request to evaluate if a specific transaction is fraudulent or not. And then there is a series of rule sets being executed in sequence, rule sets that are looking at those different aspects in order of increasing complexity. Like, for example, the first rule set is only looking at data that's within the transaction. Is a financial transaction has maybe a date that's in the past, or an amount that is greater than 1 million or 10 millions or whatever. Some data like this, which is given that itself doesn't make sense, it's easy by just evaluating that to just run a few rules and reject it, right? But maybe everything looks right in this data and you need more. So that rule set is done, and then we go fetch the additional data, the context, right? The contracts, the country, the currency, whatever. And then the second rule set is run that can operate with the data from the transaction object that was given initially, plus everything that comes from the context, right? And I guess you see the pattern, obviously, that the next step is going to go and say, okay, I have not been able to detect anything fraudulent with that data. Now I need to go and compute more aggregates. So exceed the rule engine, go compute some aggregates, like what was the spending on the last 7 days, what was the maximum transaction between those two parties in the last 10 days or 3 days or whatever. There are tons of aggregates that can be computed, but the choice of which one to compute is based on what the rule set 2 actually managed to determine, right? So now rule set 3 can try to find more reasons to go and reject that transaction, or to detect if there's fraud in it, based on this additional data that could be giving hints to a fraud, right? And then once that rule set is done, and it has exhausted basically the possibilities, then we go back and evaluate some scores coming from ML model, and then the fourth rule set triggers. So this is obviously not the full picture. There's a little bit more complexity than that, a bit more round trips, a bit more rule sets that are chained. But the point was to get the idea across that the data that's within the object is not sufficient for the decision, and we need to get more information. But because this is costly and more complex, costly in terms of processing time, we have built the system this way so that if rule set 1 already detects that the transaction is fraudulent, there's no point evaluating all the rest. We can just say decline transaction and exit right away, right? And then this way, we are basically looking for reasons to go decline the transaction as we go up and down from top to bottom in this evaluation chain. And then at the end of the rule set evaluations, if there was no good reason to reject the transaction, then it's considered to be something valid that we're going to approve, right? It takes a chance that it was valid. At least if there was fraud, we were not able to detect it in the time frame that is allowed as part of the SLA for that evaluation. So this is how it's been implemented. It's a system that we started building a few years back, let me see, something like 6 or 7 years ago. And that has been refined and improved over time, and is working pretty well, actually. For the detail, it was implemented with ODM that didn't have native ML integration. So there was a lot of code put in place to try to bring those features in place together, right? Glue the rules and the machine learning model together. So when we do that, and I don't want to drill into the detail of how it was implemented, just a concept. When we do that, basically we have some issues. First issue is each rule set is its own decision model, right? It can be a rule flow or decision model, and they are not linked together. So if you look at just rule set 2 by itself, you look at the decision model or the rule flow, some of them are one or some of the other, you don't get the full picture. You only get what this specific rule set is doing, and you don't have a global view of the overall decision. The other issue with that is the orchestration is not done in the rule engine, it's done externally. So it's a lot of, I kick off this engine, the engine does something, returns a result, I grab this result and I analyze it. And based on this analysis, I know I'm going to have to compute this aggregate and that aggregate and this one. So I make API calls to compute them. And then once I got them, I add them to some additional data set, and I invoke a second or third rule set with this additional information. So all of this glue code, which is quite important, is built outside of the engine, outside of any decision model. So it means how to change, and basically you end up coding a little bit of the logic within the code that is orchestration, the glue. So obviously this is not helping with our concern of our talk today, which is about transparency. So how can we improve that? How can we make this a little bit better? Well, idea number one, why don't we have a global decision model, right? If we have a unique decision model that has submodels using the composition, something that has been brought, by the way, by the decision model approach and the standard recently, at least not when we started this project, it didn't exist back then. But this has been brought now. So there's this idea that we can have a single decision model with submodels that are representing the various steps, but at least we have a global view. And the orchestration code that was delegated to actual code and now can be part of the decision model to make it a little bit more transparent. But when we do that, we should not forget that we also have the ability to invoke those ML models, predictive score mostly, right? And we need to also have a way to represent them within the overall decision model if we want to have a clear picture of what they are. So in the subsequent slides, I'm going to show how we would do that in ADS, because this is basically this use case led to improve this and other use cases as well, but led to improve ODM and to basically, when we built ADS, we wanted to have this native ML integration to overcome those challenges. So I'm going to show some examples that are basically screenshots out of ADS. It doesn't matter that out of ADS, what matters is a concept, right? What matters is really how we tie the two together. So in this simple example, we have a decision model. In this case, it's a decision model in the telco industry where you would want to generate offers to retain customers that you think are likely to churn, and you have a certain budget for that, right? So just go quickly across the model. The final decision of the model is what offer do we issue to a customer, and that has a specific, so the customer is one of the input that has a specific subscription, a certain cell phone plan, for example, right? So we look at which upgrade is logical for that customer, maybe add them more gigabytes or so more roaming countries or whatever. We look at how much it costs to do that, and we rank the offers, but we also look at the budget that we have to allocate globally for that retention campaign. And the budget is going to be enlightened. Obviously, it's going to depend on the customer, but it's going to be enlightened by two things that are scores. One is a customer churn, the propensity of the customer to churn, which in our case is a score. That is, so it's a prediction, right? We have no idea if this customer is going to churn, but we have an ML model that's predicting that, and we want to inject that into the rules to take the right decision. And the other ML model that we use in this case is a customer lifetime value. How much money are we going to get out of this customer in the future? Is that customer worth retaining given our budget and given all the other customers that we may have? Or are we actually going to issue a nice retention offer, like a 3 months free or whatever, or not, right? And by using this notation here, where in fact we use BKMs to say this decision here is leveraging data that is coming from outside, from, in this case, a predictive score, we have a way to inject into the decision model the linkage between hard data, right, the subscription and the customer, and what I tend to call soft data, predictive scores, coming from external models. So that's already a first step towards transparency and having a decision model that's easier to understand and easier to for the business, I think, easier to see exactly what's going on. Okay, first step. Now, what are the issues with that? We still have the fact that the predictive models are black boxes, right? I mean, the whole thing about rules is about transparency, and then we stick a black box right in the middle of it. It's kind of defeats the purpose of saying I can explain how a decision is taken, I can show you how it's been defined, if in the middle of it there is a reference to something external that we have no idea how it works, right? And also the decision model points to the ML model, but which one? Are we using the right ML model for this customer? Right, so that's also an open question. So globally, by doing so, we have a decision that is a little bit clearer, except for the ML part, right? But it's not completely perfect. So here's idea number 2. Let's wrap that ML model, that predictive score, into another small model that we're going to call a predictive model that helps us be a little bit more precise in this definition and consequently increase the transparency. So that's what we've done here. What I'm showing here is what we call a predictive model. And a predictive model is we use a regular decision model for this, right? But it embeds, it represents the signature of the call to the external model with some additional data. So where you see the BKM that says customer churn, if you click and look at how it's implemented as a specific decision model that has a few specific features. It has inputs. In our case, here's a subscription and the customer. And then we have one first decision node here where we can do a little bit of pre-processing. I'll show you on the next slide what I mean by pre-processing. Then we do the actual invocation. So this is just a hard REST call to the model, right? Nothing fancy here. It's calling out to an external system, get a score out of it, or some prediction, get that back, right? And then we have the output mapping where we can do a little bit of post-processing. So that's already an improvement. To clarify what I mean by the pre and post-processing, those are the typical kind of things that we can do in the pre-processing. So I've taken a screenshot of an example. Quite often, ML models, they are defined by data scientists out of production data. And you may end up with things where, for example, in this case, the rate plan for the cell phone service is 123 or 012. And whereas in the rules, you want to express that with values that are making sense for the business that have been verbalized properly as basic, essential, gold, and premium. I got my screenshot here, but you get the idea. So in the pre-processing node here, we can do a little bit of that. We can do mapping. We can do mapping to, for example, you may have enumerations that have different ranges in your rules and what model has been trained on, or what the data that the model uses. And you can do the same thing, for example, in the post-processing. You can do some mapping the same way. I mean, the reverse mapping, or you can do stuff such as, for example, if your ML model invocation failed, then you assume a default value, right? Otherwise, you actually set it to the value that the ML invocation return. So here you can see this is a variable. When we go here and we invoke the external model, the result of that REST call is putting the output into a local variable that can then be passed along to other decision nodes to examine it and to do something with it. So we wrap the invocation of the external score into a small decision model like this. It gives us this increased transparency, and it's very handy to do the kind of pre and post processing that we may want. So by doing that, we now have a model. I have a broken sentence here. Sorry. This is, should say now the model use is now clearer, right? So there is a broken word here. So we have increased our level of transparency. We know that we're using an ML model. We know how it's called, but what we still don't know is, are we calling the right one? Maybe we're calling a model that's not relevant, right? So there's a third idea here that we can throw here, which is, well, since we are wrapping the call of the external ML model into this predictive model, into this small sub-decision, which is itself a regular decision model, we can use that as an opportunity to add some logic to select the right model, right? Maybe when I evaluate the propensity to churn of a customer in the telco area, maybe I should use a specific model for people who are working, who are busy, they're making some money, so they don't care much if the plan is a bit too expensive, and they're working, they're busy. Whereas people who are unemployed may be a little bit more careful with their spending and may have a little bit more time to look at the competition and consequently switch plans. And depending on I've trained my models, if I've trained models, typically, I mean, you have data scientists training tons of model, and in theory, when they release a model in the wild, at least within other groups within the company, they should say this model has been trained on this type of data, and it's good for this and this type of use cases, right? Or this type of application. At least that's what they should be doing, attaching metadata to the model so that whoever consumes that, you don't want to use a model for evaluating loan eligibility that has been trained on retired people and use that for active employed people or vice versa, for example, right? So this fact that we have a little bit of logic gives us the ability to say, hey, instead of my churn being just a straight call to an ML model, it could be a call to, I may have two models, one for regular customer and one employed customer and one for unemployed customers, right? And then I can put some logic in there to say, well, if the customer is unemployed, then I want to call the outcome, that is that decision here, is going to be the result of the call to the customer churn unemployed model. Otherwise, it's going to be the call to this other ML model. So now all of a sudden, we have built this ability within the decision model to see a little bit clearer and to be a little bit more specific about which ML model we want to employ, even though both have the same signature, even though both serve the same purpose. So basically, they fit the same role into the overall decision model, which is the score of the propensity to churn for that customer, right? But the propensity to churn could be computed different ways. In fact, it could even be computed with rules, right? I could have also, instead of a call to a ML model, I could have a call to I don't know, decision table that has looking at a couple of parameters on that customer and assessing as a wild guess, because I'm experienced and I know how customers behave, that, you know, for this type of customer, maybe young people who are very savvy with the technology will churn easily, more so than older people who may have a harder time switching plans, right? So I can make an educated guess and stick that into a decision table and say, this is my model, right? Or I can use that ML model. The thing they share, though, is a signature, and they roll into the overall decision model. They have the same signature. They take the customer in, and they return a propensity to churn score out, which is the number. And they both serve the same purpose. Once I have that churn, I can compute the rest of my decision model based out of it. But I can evaluate that churn different ways. And even with ML models, if I have several ML models, it's good to have this capability to put the selection logic as part of the decision in rules. So obviously here I have an example that is extremely simple, and I've even put else here, which is probably not the best way to write it, but I wanted something that fits on the screen quickly. But the idea is that you can have that selection logic part of the rules, and also it's using your incoming data. When customer Joe shows up with employed, you're going to use one model. When customer Bob shows up with unemployed, you're going to use another model. You haven't changed your overall decision model, right? You still have a decision model that is smart enough to decide which ML model to use behind the scene. So that is really giving us additional transparency. Okay, so now great, we know which model is used, and as I was saying, which model is chosen for a specific decision or evaluation of a score that's going to be used in the decision is clearer because it is defining the roles, right? But the model is still a black box. We're calling model A or model B, but what the model does actually, hard to tell, right? It may be well documented, you may have metadata, you may be talking with a data scientist who produced it when you write your rules, so you know exactly what they give you, but it's still only just metadata. Could we improve that even further? Okay. So idea number 4 is something that we came up with, is to say, how about we take that model? Is that a question? How about we take that model and we generate rules out of it, right? We induce rules out of the model. Then we have a better idea of what's in it, right? What it represents. So this is exactly what we've tried to do. There's a project by the Dublin Research Lab. You have the URL here. It's on public GitHub. Anybody can go see it. That is basically looking at an ML model and building what we call a surrogate, that is a bunch of rules that are equivalent to the model. That is, running those rules or running the model yields the same result given the same input. At least we're trying to build the rules to be as closely semantically equivalent to the underlying model. So for the moment, it works with Boolean decision rules. So it's ongoing research, right? It's not completely baked and doesn't cover all the cases, but it's ongoing research. So that's why it's interesting. At the bottom, obviously you will have the slide. At the bottom, you have the reference to the various AI articles, research articles that led to this experiment. And the idea is to say, if we can swap an ML model by a set of equivalent rules that, given the same input, gives the same output, then we can swap by the one by the other. And when we read the model in rules, we can actually read it. Unlike an ML model, which is hard to read, or impossible to read, the rules can be read. They will not be perfect, fine, but they can be read. So this is going to give additional value to the business when they are defining the decision model. All right, so I want to exit from my presentation here and show it to you. So I have two options. I have a semi-live demo, and I have a backup of screenshots in case something doesn't work so well, or in case it's taking too much time. There's one step that's taking a little bit of time, so I don't want to show this step. So let me see. I want to go to my usual loan approval. Everybody knows this example. I'm not going to spend any time explaining what it is. We have an approval decision model here. Okay, typical, that is looking at a loan with a borrower. We use today's time. Okay, this is one of the examples of the product, right? And that decision model for the moment does not depend on any predictive score or anything. So I've already built it, but I want to show it to you. Let me see. If I go here to my folder, I have a CSV file containing tons of, I'm going to do it this way, a ton of data, name, credit score, income, loan amount, loan duration, etc. That is basically data that would be used to train a decision model. And I have 10,000 lines of that, right? All right, 10,000 lines of, well, in this case, they're all called John Doe, but they have different credit score, income, loan amount, etc., and yearly reimbursement, rate, approval, etc. So with the IME project, what I can do is I can go to the IME website, which is here, say get started. I would create a data set. So I would say add data set here. All right, browse the data set. I've done it already, so I can just, I mean, it's up to you. I can demo DecisionCAMP. Oops, sorry, DecisionCAMP. And I would add file, and then I want to browse to here. Grab that data set, drop it in here, and say next. This is running on a server that is not always very responsive, so that's why I've prepared some screenshot just in case. It's looking at the data set, it's seeing what's in there, the type of everything that's in there. Okay, so I'm just gonna go by the default, say submit, and click on this, and then I'll have a data set in there. So this is just to load the data. It's spinning a bit. This is just to load the data into, oh, okay, I clicked twice. That's why it was slow. This is basically just loading the data into the tool. And then I go rule set, and I'm going to do it, but I'm not going to let it proceed to the end because it's taking 10 or 15 minutes. Then I would say generate a rule set out of this. So I call it demo DecisionCAMP. And put a description here, choose an option. So I want to take one of the two. It does the same, it doesn't matter. So I'm picking which data set I want to use. And then it prompts me, all right, so I see that in this data set, you have all of those columns. Do I need to include them into my outgoing rules? For example, the name I could exclude. There is absolutely zero likelihood that the outcome of a loan approval, should not be induced from the name, right? Should not be derived from the name. So I probably don't care about this one. I wouldn't check this, right? So that's one thing. Which column actually matters that you want to see in your rules? The other thing is which one is a outcome, right? So in that case, approval is what you should read as a target class. That is, when you consider that this data set represents an ML model, consider that approval is the output of that model, right? Then I would pick an algorithm. So we have a couple of experimental algorithm. I'm not going to go over that for the moment. And I would say submit, and then it's going to proceed, and it's taking some time. So that's why I don't want to waste your time. I want to show you one that I've done already. It's going to come up in the queue in a few. One that I've done already, I can then say export PMML, and this gives me this. See, this is this one. It gives me an equivalent PMML that contains a series of rules, so rule set PMML, right? That contains a series of rules that are semantically equivalent, all taken together. They are semantically equivalent to an ML model that would have been trained on the same data set. And then the next thing I can do is when I'm back into ADS here, I'm going to do that as well. I can say I want to create a predictive model. So the thing that I talked about that is wrapping a call to an ML model. I'm going to call it Guilhem DecisionCAMP. All right, it's based on this data model. Fine, it's a create. All right, so we created this internal mapping model that takes an input. So I'm going to have to replace that with custom, etc. I just want to show you here how to consider that predictive model. I would say configured. And so in ADS, when we have a call to an ML model, we have two options, right? We can have either remote call. I told you earlier, we do just a hard REST call to an outgoing ML server, what's on ML or SageMaker or whatever. Or we can do a local machine learning model, in which case we run locally the ML inference engine based on the file that was passed to it. So that's what I'm doing here. I'm going to pick up that PMML file. Start here. It's this one. I'm going to drag and drop that here. I say I want to generate rules. I could also say table. I'm going to show you both. Then I do next. At that moment, what ADS does is to look at what's in that PMML and say, it says, I found the income. Which type do you want to map it to in terms of my model? Okay, I want to map it to an integer, and which one exactly? I want to map it, so those are the attributes coming from my data model. So in this case, I want to map it to the, which one is it? The income, the yearly income of borrower. Okay. I'm going to continue like this with this mapping. So I'm going to go a little bit faster just because I want to show you which one is it. This one, the amount of the loan, month's duration is, I think it's at the end, monthly duration of the loan. Obviously, this is a kind of thing where we could build a little bit of UI experience, a wizard that would pre-populate that you just have to review. We haven't gone through that yet, instead of defining everything by hand. But I mean, for this demo, it should be sufficient with 5 fields that I just define it by hand. All right, so I've done the mapping between the field on the left and all the thing coming from the PMML file to my element for my BOM, basically. Hit apply, and voila, that's it. Now I have a model. It's been reworked this way. See, as you can see, it has analyzed what was the input, the possible input, which ones are needed to make this decision, and replace prediction with a bunch of rules like this that I'm going to stop on one of them, that are looking at possible partitions and how they would be equivalent. This one is a good example, right? So it's rewriting my model as, I don't know, like a dozen rules or so, that are saying, you know, that if ever those rules trigger, then it's the same as if I had this output. So it's looking at possible output and confidence and weight level It's simulating ML model possible output based on actual condition from the rules. And as you can see, I mean, it's not completely perfect. A human would have preferred to see 88,000, right? Or 300,000 without all of these numbers here, right? So it's not perfect, but it's still readable. And maybe a policymaker is going to see that and say, oh yeah, I recognize here that this is our threshold, our famous threshold of 88,000, which come from this document or whatever, and could change the number if they wanted to. The point is that it gives us an idea of what the ML model would actually be equivalent to. I want to show you the other one. I've done it already, so I'm not going to waste time building it manually. But we could also induce decision tables. So I'm going to show you this one, in which case, instead of having a bunch of rules, we will generate just a table that contains, so this one is probably, oh, that's a rule I had picked. This one is probably easier to understand. For a business analyst, when they read this, they can probably make up what was meant by the model and understand a little bit more what the model is deciding, and maybe decide to keep it this way, right? Or maybe decide to rewrite this, refactor this in a way that represents more the company policy, or that is, oh, damn it, we depend on the rate, we should not. That model is not good because it's dependent on this, it should not. That's because that's the whole thing, is that with rules, we can guarantee that there's no bias, right? If you approve a loan based on this and this and this, but you should not be using some type of data to make such a decision, but maybe you're going to realize that your ML model actually was using this kind of data, even unknowingly, just because the way that you curated your data initially and you train it, it happened to catch onto that data element when you should not have. And by seeing that into the rules, you can realize if your model, the quality of your model. So that's where we are. And as a conclusion, what I want to propose here is that this is an ongoing research project, right? It's obviously not a complete, perfect feature that is rock solid and that works in all cases. It only works in some specific cases, and it's based on some research algorithms that are being evaluated and improved. But still, it will bring some transparency. It will also help, for example, when you retrain a model and you regenerate the rule induction, for example, the decision table after retraining based on additional data, and you compare the two, you can see if that had an impact or where are the changes. It generates rules that are far from perfect. As you can see, they still require a human being to sit in front of that and wonder what does it mean. You know, is it useful? Is it really reflecting the policy of my company? But we think there's value here, and that can be, so I know everything has been about LLMs and beefing up the foundation model to make them more powerful, etc. But this is another approach. This is an approach which is to say, how about we could have a window and pick into an ML model and express that as rules so that it can be mixed in a way that people can understand what the ML model is doing, and that the overall decision model that contains call to ML models is actually more transparent, more easy as an interchange format between various stakeholders in the company to make sure it's more complete and it's giving you the full picture of the decision that's taken. And that's about it. So that's really what I wanted to present today. Jacob, you told me to shoot for 45 minutes, so I think I'm pretty good here. Tell me if there are questions. Can I see them actually?
Yeah, try Q&A, but I can read it. Thank you very much, Guilhem. And one question comes from Jan Purchase, who mentioned that this is kind of what they did in DecisionCAMP 18 when they used Reaper integrated in the rules-based environment. And his question is about, first of all, about Reaper, and I also would add to generate compact rules, which algorithm do you prefer, Reaper or anything else. And another question Jan has for you, is the surrogate really semantically equivalent to the regional ML model?
Yeah, I see the question now, indeed.
Okay.
So the first one is about DecisionCAMP 2018. Frankly, honestly, I'm sorry, Ian, but I do not remember all the sessions in that. But I will go and look because I didn't remember that was presented. Reaper was presented back there. So how does it compare? It uses Reaper as one of the possible algorithms. I don't know if you remember where I was showing the creation of the rule set from the data set. You could pick BRCG or Reaper, which is one of the algorithms that is used internally. But there's more than just that. There's been a lot of research on that to actually go from data sets to rule set expressed in the ADS BAL format with on top of an ADS bomb. So there is a lot of, it does include Reaper, but it's not just Reaper, right? Is a surrogate semantic equivalent? As much as possible, yes. As you could see, there were some rounding errors, some interpretation. In fact, there is also a thing about the size of the dataset. When the dataset is relatively small.
Guilhem, are you actually saying that you can take any ML model, like a vast neural network, and essentially completely model it using a set of rules in this way? Because most of the techniques I've seen to do this are only generating an approximation. They can't be completely the same.
Correct. That's what I'm saying. It depends on the size of the data set. If the data set is small, then in a finite amount of time, like for example the one I've showed you here, we can obtain a set of rules that is almost equivalent. But what we do is that when the data set is bigger, we do put a time constraint on the generation, otherwise it's not practical. And then we run algorithms that are mostly optimization algorithms to try to find a set of rules that match as close as possible. But there's this notion of error, right? We do that iteratively by trying to reduce error and try to be as close as possible, but it will not be 100% equivalent. And that's also, I mean, it would be wrong to just take that set of rules and say it's equivalent, just run it, deploy it to prod this way, run it. It's not designed for that. It will not replace the ML model that the way it was trained. And the ML model has probably been tested, validated, deployed to prod or whatever. You cannot just take that, spit out 10 rules, 20 rules, 100 rules, and say it's equivalent, let's run that instead, right? That you would be taking a chance that it would work a good chunk of the time and not sometimes. What you want to do instead is show that to the business. It has value to show that to the business to enlighten.
That was my last question, which is, what's the approximate relationship between the size of the surrogate rules and the data set that trained the model that it is a surrogate for? Because I have to say my experience has always been that sometimes they can be very succinct, and sometimes they can generate enormous surrogate rules which are hard to interpret by a human. I wondered what your experience of that was.
Yeah, we've seen that as well. It depends on how the model is structured. Sometimes it generates just so many rules that, I mean, you cannot do anything useful with it. With those rules, you show them to the business user and they're just lost, because even if you have just 100 rules, it's a lot, right? That's also why we like the decision table format, because it's more compact, it's easier to read for a human being. But if there are too many rows or too many cases with blank cells and everything, it becomes unmanageable. So in some simple cases, like the one I've shown you today, it is useful. I don't know yet how well it's going to scale and what kind of improvement can we make. Sometimes you can have rules that are subsuming each other, where one rule is looking at a range and another rule is looking at a bigger range. And maybe you can approximate it by merging the two, and you're going to lose a little bit of precision, but you're going to gain a little bit of clarity in the resulting model. And that's exactly the kind of research that we are looking at to try to improve this output, even if it's a little bit less precise, but more usable, more transparent to the business. It may actually have more value, right? So that's what we're looking at. I cannot have a definite answer because obviously it's ongoing. I'm going. Oh, Jacob, I see you posted the link here. I'll go check it after this.
Okay. And if you click on new posts, you will see a very interesting request for Gary, who wants to apply ChatGPT to CSV file and see if ChatGPT will come up with new rules, and maybe they would be similar or not, without talking about which algorithm to use. So what do you think?
Yeah, definitely. Gary, I will email you that file. It's not a secret file. It's actually posted on GitHub. So as one of the samples for this rule induction research. So I'll send you the file, no problem.
Yeah.
It will be interesting to see what you come up with and how it compares, because that's another area that I guess everybody's exploring. It's LLM inducing rules.
Gary, we have a complete set of downloadable files. If you go to rulelearner.com, very similar files you can get from there. Just download and apply them. It's interesting. But one comment about what Jan asked in DecisionCAMP 2018, when we discussed similar topics, this question already was raised, and I remember me and Carlos came to agreement after analyzing more than 20 different algorithms that usually Reaper produces the most compact set of rules. It doesn't mean the most precise, but C4.5, it could be usually much larger set of rules and less understandable rules, but sometimes quality is better. So it's really important.
We've seen that too. You're right.
Yeah. Right? What is important to set up just experimental environment, graphical interface, similar to what Guilhem just presented, so users can choose which algorithm to use and how to experiment, and then automatically generate rules in form of target requirement, PMML or Excel rules or any other format that the rule engine can understand. Any other questions?
Sorry, that's one of the things that, that's why I also wanted to show you this, is that by integrating the tool within ADS today, where it generates actual rules that are in the language of ADS, based on the BOM of ADS, etc., with a simple wizard that you can go through in a couple of clicks, it gives us the ability to experiment, because all of these are very valid questions. We don't have the answers for those, right? It's going to depend on data sets, it's going to depend on how you tune the algorithm, how, bunch of things, bunch of parameters that depends on the actual data that's in there, right? And we want to have this ability to experiment. So now we have an environment in which we have a quick feedback loop between data set, algorithm, and rule induction, and that's what our researchers are using actually to tune this as well. Hopefully one day it's going to be a tool that's can be made available, right? Today it's still very experimental. It's good for us in this community because we tend to be at the edge of what's going on and share about sometimes academic results and things that we're working on that we think are interesting to the world. But it's not yet to the point where you could just make it a feature of the product and hand it out to anybody without a lot of caution warnings before using. But we have this ability to experiment, so I think that's useful.
Okay. Yeah, some products already have it, not experimental, and actually we have in real world production similar things, and probably Sparkling Logic can tell you the same. Jan probably, Jan Purchase has the same. But you made very important point, and I want to stress this for people. When you said you're not only producing rules, you're producing meta information about the produced rules. It means your decision table can analyze this information and make decision how they can trust these produced rules, or maybe to use some default values, and even more, business users can adjust them and can use this meta information for their understanding of with their context knowledge to which rules to apply, which rules to adjust, or maybe ignore these rules. Because rules is not one-time operation. They always in ever-learning environment. And maybe rules produced yesterday would be different than produced today because the CSV file is not static. It keeps changing all the time. And your rules, just orchestration rules, should be smart enough to select, like Guilhem pointed, which ML model to apply.
Yeah.
Okay. If we don't have any more questions, Guilhem, thank you very much. Very interesting presentation as usual. And after 4 very serious presentations, we deserve 1 hour break. And we will get back exactly at 2 p.m. New York time. And it would be a presentation by James Taylor. And please take your time, relax, and we will continue. We will have 3 more presentations after the break. See you at 2 p.m. Thank you.
Thank you.
Jacob, stop the recording.
Yeah. Yeah. Let me stop recording. Thank you.